let's see. Great to see everybody. If you're here for a very deep technical talk, you might want to just leave. I won't go into too many deep bits and bytes. I was curious to know how many people have heard of OpenFlow. Great. How many people actually know what OpenFlow is? Great. Good. I'll talk a little bit about that. So I'll get into some bites on that. In general, is there anybody who's thinking of Erlang? Anybody thinking of Erlang in the context of software-defined networking? Oh, great. That's excellent. So I gave this talk at TechMesh. Did anybody see that talk? Okay. Which was in Europe in November. It's slightly modified. I'll try to hit we end at 11:25. So I'll try to stop at about in about a half hour. I won't go in depth into all the slides. My main goal is to just start a conversation, find other people who are interested, let you know what we're doing with respect to messaging and networking and OpenFlow and Erlang, and so I'll try to leave some time at the end. So I'll jump right in. Okay. So who's heard of Infoblox? Anybody heard of Infoblox? Oh, that's cool. All right. So we are deep in the bowels of enterprise and service provider infrastructure. We do network automation and DNS and DHCP and all this stuff that is not at all particularly cool or sexy. We have a large-scale distributed data platform, which we call the Grid, which is not based on Erlang today. But just to give a little bit of motivation of why we're interested in these kinds of things is that we have to think about how to scale a large data information processing platform. We happen to deal with kind of network-centric data, but you can extend that to Hadoop and other big data processes. So that's something that I know a lot of us are thinking deeply about. The sizes that we have today, 250 members per grid, where really one low-level technical person can manage that, whether it's 200, 1,000, or 10,000 members in this distributed grid. Our customers require no technical expertise. So if you have a PhD in computer science from Stanford, you're not going to go work in the IT departments that are deploying these products. So we have a requirement to be able to deploy that kind of scalability and have it be completely embedded in a sense in terms of a solution. So we started thinking deeply about that. And really, when we thought about how do we scale that, the kinds of numbers that are of interest to us are things like the Internet of Things. Now, I put this slide together in November. That's before Cisco started pushing the Internet of Things, if you're watching that conversation. But what that means is really a scale that's several orders of magnitude larger than what is really practical today. So we don't think of that as a strange research project because of the exponential increase in power that we're getting per dollar. So these aren't crazy numbers. And I know for you, they're not crazy at all. For a lot of you, how do we scale to 1 million cores in terms of processing power? And as everybody here knows pretty well, that's not at all science fiction. Google and Amazon have been doing that for a long time. So the question is, how do we bring that into a more industrialized framework? The other thing that's really disruptive from a kind of industrial use case perspective is this model that has been very well understood in the cloud companies, but isn't well understood in many other venues, which is what kind of Joe and, again, it's great talking Erlang folks get right away, which is the hardware is just failing all the time. That's the model we want to have, right? And so I was thinking, well, Java always said, write once, run anywhere. I suggest Erlang or something similar should be write once, run forever, right? And it doesn't mean I won't modify the code or change it, but if I don't want to modify the code, I shouldn't have to change the code just to upgrade to new hardware or whatever. So there you go. Write once, run forever. So of course Erlang is closer to kind of providing the properties that we're looking for from an industrial solutions perspective, I would say nothing has all the properties. And you know, but Erlang is certainly as close, if not closer, than anything else. But what about the network? So, you know, I think Joe's talk was coincidentally, I think, well dovetailed with a lot of things we're concerned about. You know, when we're talking about, you know, scaling to 1 million cores in a data-intensive system, the network really becomes a source of complexity that is absolutely fundamental to thinking about scale. And, you know, I don't know, I'm sure several of you have tried to run clusters of relational databases with full ACID transactions, and you kind of hit that 30-node barrier. And then you say, okay, we go to a NoSQL store, which really allows us to think about scale in a different way, but we're throwing out consistency and transaction mechanisms which are completely okay if we're doing social networking and other things, and it's all right if I don't know whether, you know, I added 100 friends. If it takes like another day for my 100 friends to show up, who cares? But when we're talking about coordinating systems in an industrial application, some kind of transactional consistency is generally required. So, you know, we look at the world as having a spectrum of that. This really just brings up a lot of issues in timing and connectivity and complexity in the network. So how do we deal with that? And that's been a puzzle for us for a long time. Of course, my background is in high-performance computing, and you know, how many people are very well versed in Infiniband? Okay, so Infiniband's a great technology that solves a lot of problems. It really brings a lot of network control close to the application. You can think about you know, providing properties into the network from an application-centric point of view, but it's really quite expensive. And Ethernet 1, you know, this is 2013, and other than a niche kind of application, it's unlikely that Infiniband is going to take over the world in the way that would be required to drive the prices low enough to really be important for wide-scale industrial applications. So again, we turn back to the few who've really have hands-on experience at tremendous scale and see what have they done that they're willing to talk about, and where are they headed with networking. How many people are familiar with the Open Networking Foundation? Okay, anybody members, or are there any members? Okay, so not very many. So this, I'll just say a few words about the Open Networking Foundation. This is a standards organization, the board of which is Google and Facebook and Yahoo and Verizon. So if you're in the networking industry, this is kind of mind-blowing. There's a networking standard that's really being driven by consumers, not vendors. So kind of in theory anyway, this has more kind of consumer advocacy properties than other standards organizations. So that's interesting. And then they own OpenFlow, which I would say is the kind of, well, I'll talk about where OpenFlow sits in this kind of market clutter of software-defined networking. So the Googles and Yahoos of the world have been focused on software-defined networking. There's the standards organization. There's this thing called OpenFlow. There's also Quantum and all this other stuff. So a real big, and there seems to be a lot of market, you know, it's like cloud was, right? What's cloud? What's software-defined networking? There's a whole lot of definitions. I don't think it's an important question. I think the important question for, you know, what we're interested in is really exploring this question, which is what is hardware-defined networking? And my suggestion is a much better way to approach the question of what's software-defined networking. Hardware-defined networking, this is not a technical issue. It's an entire industry that's organized along box function lines. So when we think about building a network today, generally, we think about going and buying boxes that are dedicated to some set of the 2,000 protocols defined in the IETF, and other functions. So whether that's a load balancer, a WAN optimizer, a firewall, a traditional router and switch, and a huge economic system is built up around this. So everything from how the media classifies companies, the way Wall Street classifies companies, the way venture capitalists invest in companies, the way the products are marketed and rolled out, to the way the consumers are trained and deployed. And so you have a cluster of manual activity around each one of these types of boxes. I have my firewall team, I have my load balancing team, I have my router and switch team. Now in smaller teams there's a lot of overlap, but the knowledge tends to be bucketed into these box function lines. That's striking. In reality, today in 2013, the technology in each of these boxes is virtually the same. Ethernet 1, and there's a lot of fast processing available. So the main differentiator today is software in reality, but the consumers, for the most part, except for a few who built it all themselves, most consumers are not gaining the same economics of fast, cheap hardware at the networking level that's generally programmable, right? I can buy a box, and I don't know whether I want it to be a firewall or a load balancer or a WAN optimizer or anything else before I buy it. I buy it just like I buy a server, and I buy like 1,000 of them, and they're priced just like servers because I can buy 1,000 servers for a very reasonable price. And then I put them in my infrastructure wherever I want to put them into, and then at real time I can think about what functions I want them to have. And now actually my space of possible networking functions just really opened up, because I don't have to think about it being a firewall or a load balancer. I can think of the properties I want, which is probably some combination of those and many more, like contract checkers or something, right? So finally we could potentially have a programming substrate which then unlocks this value, right? So it just changes the model. That kind of, if you imagine that, then we get back to the question of what is software-defined networking? It's a market correction, right? This is a way to get better economics into the consumers of networking, economics that are much more similar to servers and PCs and tablets and that stuff. Cheap hardware, software, which is great when we then think about software, write once, run forever. That's what we want in networking. So the last time we saw this kind of big shift in value from software from hardware to software as the center of value, doesn't mean that there's no hardware. It means the hardware is generally programmable and cheap. The last time we saw that is in the end of the mainframe and in the end of the mini and in the emergence of PCs. So software-defined networking is not kind of like a phenomenon happening around networking in the cloud or data centers. Those things are tremendously important first use cases for dynamic networking, but you can see that the implications of changing the economic model mean that really we may be faced with many more choices about how we think about communications going forward, and I think that will impact how we think about distributed computing and the potentials we have. So it's a very exciting time, and you're not too late. It takes not necessarily a long time once it starts going, but it's a significant event to have a whole economy change from a hardware center to a software center. So there's lots of opportunities to get in on that action. Okay, so that's kind of the very big, broad picture of how fundamental this is to what's going on. I want to talk a little bit about the actual bits and bytes for those of you who aren't familiar with OpenFlow. So this is like a really probably poor OpenFlow 101 tutorial. There's lots of resources, and we can delve into that later. So here's legacy networking. There's really two centers where you buy products in legacy networking. I know you know all this, just to say it out loud. You have what we call data plane products. Those are the hardware boxes I was talking about. Firewall, load balancer, router. It has something generally called a control plane that's baked in, right? So that would be like BGP or OSPF, something that's kind of making decisions about the state of things. And then you have a management plane. So in general, you're buying boxes that have a specific function in the data plane, in the forwarding layer, and then you're buying overlay software, which is really only, it's just historical in batch. If the management plane goes down, there's no problem, right? I mean, there's a problem in like a day, right? Like, oh, I'm not getting the statistics I need, I can't configure things, I can't deploy new boxes, but nobody's business is actually disrupted in real time if there's a failure in the management plane. It's all about this boxes. So this is kind of the hardware-defined networking picture that we had. There's absolutely no application awareness. It's completely labor-intensive to deploy and manage, and there's really one kind of set of stacks on which it's all built on today, which is TCP/IP, which is great, right? But there's a whole kind of spectrum of messaging or of communications technologies that could happen. Okay, so now let's look at a contrasting view of the world, which is the kind of software-defined networking view from this programmable hardware perspective. So this is not to say that northbound interfaces and cloud interfaces and quantum aren't important. I'm just having a very specific focus on this big implication of a change at the economic layer. So now, instead of the embedded control plane and the management plane, we have a cheap general programmable forwarding plane. So these are general. They don't specifically do TCP/IP. They don't specifically do firewalls. They don't specifically do load balancing. They're all general. These red lines here that cut across them are flows that cut across those. And that's just, what's a flow? It's a whole stream of Ethernet packets. So one way you can think of this is it's a big layer 2 mesh of Ethernet things, where I can now do things to those Ethernet packets in real time. And I have a controller which is logically centralized. Good example of a logically centralized but completely distributed system is DNS. So we know that doesn't mean it's actually centralized, but it's logically centralized at some level. And we have a standard interface to actually program the behavior, the reaction of any particular forwarding element to a flow, to a packet, in real time. And there is a standard that exists today like that, and that's called OpenFlow, right? So instead of thinking box function, box function, box function, we think here's a flow, let's call it 1, this is flow 5, this is flow 10, and guess what? This box should tunnel flow 1, this box should meter flow 1, this box should switch flow 1, this box should NAT flow 10, this box should switch flow 10, this box should tag flow 10, right? And if in the next minute we want these boxes to do different things with those flows, we'll do different things with those flows. So now we have a flow-centric programming model on an inexpensive forwarding plane. That's a radical shift in thinking about networking. It's a very, very different shift. So we think that's exciting because if you think about large-scale distributed systems, having this kind of control over flows in real time suggests some possibilities to fix some scalability and performance problems that have been plaguing us doing large-scale distributed systems for a while. So that's a kind of very basic primer. I won't go into this too much. I mean, this is just the same thing again, a little bit more in-depth example. So I have OpenFlow switches, and you can imagine, again, other protocols. OpenFlow switches, the controller is just some software sitting on a PC or a cloud or a cluster or whatever you want, some programmable element. And I actually have an application developer who now in some way can say, okay, I have an idea because I'm not just a client-server developer. I already am thinking about like 20,000 things, right? So I have some ideas about how those 20,000 things should share messages. I want to put code at the controller level that actually does things with the messages between those 20,000 things. And I think the thing that makes it kind of timely today is what Joe alluded to in his talk, which is really from an industrial perspective, what's been the most valuable thing, there's nothing wrong with it, it's just been the most valuable thing over the last 20 years is client-server computing. And in client-server computing, the network from a programmer's perspective is trivial, right? You really don't have to think about it, right? I just have a client and a server. And if my server is like 20 million servers, conceptually it's still a client and a server, right? So I'm not really thinking deeply about a complicated network. But if I'm really doing, okay, I want to program a swarm of robots, right, like 20,000 robots, maybe there's something fundamental about, or processes or virtual machines or whatever, there's something fundamental about communication, which as a programmer, I kind of want to have the abstraction and ability to control. So OpenFlow points us in that direction. In the same way, I think Erlang points us in that direction. So then, yeah, oh, my packet does something. And OpenFlow, just, it's very simple, right? It's like I have rules. I can match, right? So pattern matching. I can take actions. I can collect some statistics. So it's very, very straightforward, and not surprisingly well aligned with Erlang, because Erlang came from a communication-centric problem. So those things work well. So we've been doing this for, kind of very interested in these intersections for, I don't know, 18 months or something like that. We started a site, it's just very early, called flowforwarding.org, which is completely open source, investigation, really, of OpenFlow in general. So I'll talk a little bit about it, but also specifically we're interested in the intersection of that and Erlang. So you can go there. Currently, we have two main projects there. One is LINC, which stands for LINC is not closed, in the great tradition of recursive acronyms. It is it's a OpenFlow soft switch that's written in Erlang. And Michal actually is one of the primary architects, so if you have very deep technical questions, that's the guy you want to talk to. We actually contracted Erlang Solutions to do that, and we're contributing that back to the community. We're not interested in monetizing that at all. We'd love for that to be expanded and worked on. So that is investigating using Erlang to do OpenFlow switching. It was written from the ground up. The kind of, I'll talk about the other switches in the market and the difference. So we have that. And then we're trying to kind of prove out some of the ideas by some work doing acceleration of Hadoop using OpenFlow and LINC. This is very early days. These are very, so if you're interested in these, you can talk to us. There's some folks mainly in networking who are contributing to this. We're always looking for industrial contributors, collaborators, whatever you want. Just in the interest of time, I don't want to go too much into this, but there's lots. If you're getting interested in OpenFlow, there are kind of all different types of OpenFlow switches you can start playing with. I've listed here, without going into all the details, kind of the four big primary switches. The most commercially viable OpenFlow switch is Open vSwitch, which is actually just a virtual switch which supports OpenFlow, has very good support in the Linux kernel. And so if you're kind of wanting to it's written in C, if you want to, kind of play with OpenFlow from a commercial perspective, that's probably a place to go. And then there's three, I would say, more kind of either prototype-oriented or forward-looking switches. Indigo Loxy, which comes out of a company called BigSwitch, being supported there. SoftSwitch, which is also an Ericsson project, but a C implementation around prototyping, and then LINC. And so for LINC, we're interested in a couple things. One is multi-core, bringing multi-core to the switching platforms. So what if a switch, for instance, if this generally cheap programmable switch, we're really just a big multi-core box with like 32 ports of fast, gigabit Ethernet on it. What kind of architectures make sense for making that? And maybe it's Erlang. And so if you're kind of interested in Erlang and the abstractions for Erlang to doing that, LINC is a good choice there. interestingly, Erlang, LINC is because here's a unneeded for you, this audience plug for Erlang, but just so everybody can feel good about Erlang. Because of Erlang, you know, LINC supports all the OpenFlow, Open Networking Foundation standards today. So it's the only switch that supports OFConfig, which is a configuration management, and OpenFlow 131, which is the latest version of OpenFlow with a lot less resources because, you know, of all the great productivity properties of Erlang, it being a functional programming, et cetera. So that's kind of exciting. It's still really slow, so I'll talk about that. So we need to make it faster. Anybody who's interested in helping with that's great. Maybe I'll just spend a couple minutes on this. This is the LINC switch architecture. This comes right out of the OFConfig standard, which is a configuration standard, which is a companion to OpenFlow. And this is the thing I want to highlight here is this blue box is called an OpenFlow capable switch. And inside are what's called OpenFlow logical switches. And so you can kind of think of the blue box as being one of these very generally programmable hardware pieces, right? Could be a server, could be virtual. And then there's actually lots of OpenFlow switches that can get instantiated inside that, right? Doing this kind of abstraction turned out to be really straightforward. Well, I'll let Michal say yes or no, but it's from looking at other implementations I have, this is one of the we've looked at, it's so much more straightforward in Erlang because of again, the conciseness and abstraction. So that's been nice. We've also architected it so we can hopefully make it fast, right? So we have a few different options for putting a fast path underneath. If anybody's worried about performance, I poured coffee for my wife this morning. I collect mugs of computer companies that are now defunct, right? So I have like Sun and Digital, right? And I poured coffee for my wife in a cup that was a Digital Equipment Corporation cup, and it had this cool, it has a little computer on it, and it has a screen that's black, right, until the cup gets hot, and then the screen shows something, and it says, Alpha XP, the most powerful PC in the world. I said, that's right. Who needs the most powerful PC in the world? No one, right? That's why the Alpha PC, what we need is the least expensive PC that does our job we need it to do, right? So that's the era for networking that we're just coming into, right? This is not about, man, we're not going to be able to get line rates. It's like if the hardware is inexpensive enough, we'll have enough of that, and it will be, well, there'll be too many. But we know how to program lots of things. That's what software is all about, right? So we're just entering this era where we think about networking in a completely different way, which is it's everywhere, and it's fully commoditized, and we completely can program at any time. And if you talked about having a home PC or a server in 1975, people said, as you guys know, who would ever want that, right? What would you do with that? So we're in that same kind of place in networking. Wow, what could we do if we had all of these cheap, inexpensive, fully programmable boxes everywhere? That's pretty mind-blowing. So we don't worry too much about performance today, right? And but we think that it needs to be just fast enough for the class of applications that make economic sense in terms of deploying these things. And Erlang is a great kind of multi-core, because we know there's going to be more and more cores, right? Let's take advantage of the multi-cores. I'm not going to say why Erlang OTP, but I will say this. One thing is great about the communication roots of Erlang as opposed to the cloud computing is that the bit syntax is awesome. Because if I think about wiping away, because what am I saying? Am I really saying that we don't need well-defined protocols? Yes, I'm actually saying that in networking, right? Which is very heretical in networking, but has been commonplace in the web for a long time, right? JSON's like, what, de facto, right? So in networking, the reason that we have 2,000 RFCs is, and that really carefully detail every state machine and everything like that and all the bits and everything is because the fundamental assumption is to make communications go fast enough, we have to spin custom ASICs, application-specific integrated circuits, so we have to have custom hardware. If that's not true, then we really can think a lot more liberally about protocols. And so the networking protocol stack may look a lot more like the cloud communication stack, which is a lot fuzzier than anything coming out of the IETF. But we still want to operate at the level of bits, and again, this bit syntax is absolutely, coming screaming out of the late 80s, is suddenly extremely relevant, which is very, very exciting. So again, for the interest of time, I won't go into too much, but we have basically for our Hadoop acceleration, what we did is we said, okay, for for big data problems today, for most people, the problem is still in the storage I/O channel, right? That's where the bottleneck is today. Disk is slow still. That's changing with SSD and everything else, so we see networking as a frontier problem in large-scale distributed data-intensive problems. And so if you assume lots of very, very fast memory, which is not unreasonable to assume at all, the network really starts to choke up when you go to 1,000 or 2,000 cores to try to compute one good MapReduce number. So again, coming back to Infiniband, the idea is, there's plenty of people who put Infiniband in, and it works. And so the idea here is, does OpenFlow on top of Ethernet give you like 60%, maybe, whatever it is, of Infiniband at 1/10 of the cost? Because if that's true, it's a win. So we're interested in that. So we actually deployed Hadoop and put the LINC OpenFlow switch in there and started measuring things. These were published at Supercomputing 2012. And we're continuing this research. If you're interested in these kinds of things, love to talk with you and collaborate. We have a graph that is a little bit better than the red line. I don't know what that means, but it's good. Okay, no, you can look at the paper. We're in early days. It means that it's trending in the right way, but it's just not fast enough for production today. So here's possible roadmap items for LINC. So fast forwarding modules. We really want to think lots of cores, lots of cores, lots of cores. It's a big ambition of ours, hopefully this year, to get a do-it-yourself kit. How many people have a Raspberry Pi? Yeah, if you don't, go get one. It is like 1980 all over again. There's this do-it-yourself option now in networking that was never there before. We'd love to have a kit that you can buy, build your own OpenFlow switch for less than 5,000 bucks, right? And have it do something that's relatively useful, right? Like the PC in 1980, relatively useful. We're not saying that this will replace every single big router, switch, or firewall in the world, just like there's still mainframes today to do, but there's something fundamental happening. And this last thing is really, my dream I hope I can excite at least one person in this room or in this conference to do, which is, can we get this kind of fine-grained programmability embedded into the OTP itself? Right? And we'll work hard at trying to understand what are the right abstractions. But then I have all the pieces, right? Because I have a distributed system, and now I can think about laying down network properties in some nice abstract way, which relates to whatever job I'm trying to actually do in real time. So that's a big, big dream. Maybe you'd be interested. So I won't go too much into this. There are 3 kind of approaches we took in trying to make, this is just for anyone who's really interested in networking and pointers in the right direction. For if you download LINC and start thinking about it, here's what we've been thinking about. There's kind of 3 directions for making LINC fast. One is to use something like DDIO from Intel, so this is a picture that says core 1, core 2, core 3, core 4, core 5, core 6, core 7, core 8, and it's got a couple of Ethernet ports here that have the ability to bind to specific cores. So can we put the fast path, bind them to some specific cores, and spread the rest of the LINC functionality across many cores? So that's just one option. We'll share the slides. You could just have a straight SMP kernel, so now the LINC switch, the Erlang switch, goes across all of the cores, and we don't do anything special. This is particularly good in hypervisor type options. I think we're going to explore this very aggressively. And then possibly with a programmable hardware fastpath. So there are some of the hardware companies that are coming up with very large TCAMs and other kinds of very exciting things. And you know, the danger here is they have to be as de facto standard as the x86. So we're not very interested in like, okay, we have this one special card that's really fast and it's $8,000 a port. You know, that's not helpful. If it's like $10, you know, a port for 100 gig and you know it's really cool, that's great. So we're really interested in how does the hardware commoditize. Okay, so just leave with a couple things. I mentioned this before. You know, I think these are wide open problems. So we've worked with, we're collaborating a little bit with Princeton University on Frenetic, which is a programming abstraction that uses reactive functional programming, which is kind of like how do you get rid of all the callbacks, to think about how to program the network. I think the contract checkers is an interesting idea. So we're trying to understand what are the right abstractions that we want to expose to a programmer. There's lots of opportunities to contribute there. And you know, I was at TechMesh, and the Haskell guys were like, I/O's a side effect, right? I'm like, how is that possible, right? It's a pretty big side effect, you know? It's everywhere, right? Because they're like, every time I/O happens, it may cause dizziness and headaches, right? So we're going to shunt it over here, you know? And I think that's a really, really limiting, that is a computation is king viewpoint. And I think that that is absolutely appropriate for, you know, 90% of the industrial applications that have kind of been important, or 90% of applications up till now, client server. Again, the network's trivial in client server, so it's reasonable to think that way. But, you know, what about communications being completely fundamental? What about having things like Joe's contract checkers? You know, this is a picture of a swarm of flying robot-y things, right? They're going to have to communicate in a fundamental way. The computation is not king here. The overall network communication is just as important as the computation. So it doesn't seem reasonable to think of I/O as a side effect, but something absolutely fundamental. That's a swarm of fish under there, right? That's the kind of properties that we want to see in terms, and the right abstractions to be able to program them very simply, right? There's no mainframe operator I have to go talk to get my 8-core, you know, machine to do awesome things. I shouldn't have to go talk to a team of security specialists and CCIEs to get my, you know, collection of things to talk to each other fundamentally. So that's what we're doing with Erlang and OpenFlow. Here's some pointers. You can send email to info@flowforwarding.org. You can go to the website. You can download the code. It's on GitHub, and take it from there. And I think that ends my talk with 5 minutes. Any Any questions? Joe? Yeah. 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 Yeah.
Needs one type of software, and the data plane needs another type of software. This is FPGAs and God knows what down there, and DSPs, and this is high-level protocols. And the nature of those two is so different. The different programming languages should be used for them. And this is what we've done for 20 years. We know it works. So we know the result of what you're going to do will work because we've been doing it for 20 years.
Yep. And messaging architectures too. People have been doing messaging, large-scale messaging. They look at OpenFlow, they go, we've been doing this. We go like, exactly, right? But what's changing is the economics, the ability to do that at scale at the most fundamental level.
The other thing, presumably, correct me if I'm wrong, but because you've got these OpenFlow networks, I worked a bit in research and did things like overlay networks. So overlay networks won't be, I mean, you could put a peer-to-peer system with a distributed cache table down at the networking level,
Yeah, it really opens up the possibilities, and so then that's also challenging too, because it means that the way that we've been thinking and rationally planning and engineering is getting disrupted. So one question is, all those things are possible. What are the right abstractions? And most importantly, what are the killer kind of use cases that are really driving those requirements? And we're starting to see that with cloud and big data and Internet of Things, but it's not clear what, if the internet was important but the web made it really critical, it's not clear today what is the killer use case that really drives this model and drives the economics. Any other questions? Yep.
You have a Cisco cup sitting at the back of your cupboard ready to take out one day.
Yeah. Yeah, I'll invite you over to my house. You can check it out. I think it'll be challenging for, it's very disruptive. It's very disruptive across the board. But the reality is that just like anything, it's disruptive across the board, right? So who's going to think this way? Who's going to program? How are they going to deploy it? So, we're not too, we're pretty early days.
Yeah, I've been following this for a while, but it's hard to get my head around. It's, I don't really see the possibilities. So many people obviously got it, but I'm really struggling to.
Well, yeah, I'm not sure a lot of people have it, to be honest with you. I think that if you build cloud systems, right, that your network has to have different profile. It's not clear, though, about the economics, right? So I think that the initial use cases for very dynamic networking make sense in the cloud context. I think when you start to see, and is happening, when you start to see these generally programmable, inexpensive hardware platforms, that's my suggestion, everybody. Just watch for that. Watch for these kinds of software stacks. Get them and start playing around with them. We haven't had this opportunity where there's really a new hardware abstraction, a new platform for computing since the 80s. I mean, we really haven't. So the possibilities are both very broad and also not understood because we haven't have enough hands-on experience. So this is exactly the kind of community that can start to, as these products appear on the market, and you already have 90% of what you need by being an Erlang programmer and understanding how to think about distributed systems. There's a lot of opportunity just waiting to happen. But I don't think you're alone in not getting it. Great question.
So probably the reason why no one is getting it, myself included, is that probably we haven't seen a scale at which it would suddenly start better.
Yeah, this is a great question. So let me just. So the question is, how big? Isn't this just for the big guys, right? That's the question. And I think if you go talk to Alex Ganaris from Concurrex, he'll tell you, wow, what they did, the kind of capacity they had in a Facebook data center, in whatever 2005, we can get into like 17 blades today, right? So the subtending this whole thing is a true. You guys are mostly engineers. It's an exponential growth in hardware power per dollar on a 18-month basis. That's continuing to happen. Exponential growth is a big deal. So we really, when we talk about scale, that scale from a computing power and a multi-core, like 64 cores, is here today. I think the question is not how big do you have to be, but what problems require you to have this tight coordination. So I have a very concrete example. I think about Hadoop again, and let's not worry about Hadoop, but big data processing in general, like a MapReduce framework. Right? So for those of you familiar with MapReduce, there's these different phases where you're going to do computation in a distributed way, and then you're going to aggregate results. And the problem with the aggregating results is you have n machines, say 1,000 machines, that are coordinating to compute one number. Right? So if one of the machines has an aggregate result, which is not a very big packet or anything, but it's really delayed, it's like having a fleet of buses and one guy missed the bus and he's got to wait a half hour for the next bus, but you need all the people at the endpoint to get to the next phase, you have this kind of blocking delay problem. So we want the network to go, whatever you do right now, just for the next 10 seconds, make sure that every one of these packets gets to where they need to go at about the same time. So those are ordering problems that have nothing to do with bandwidth, right? And this is, I think, in the applications where complexity is really the barrier to scaling, the wall clock time, because we still want to get that wall clock time, where the complexity is the barrier to scale, those are the applications that require these properties. That's where this will be most useful earliest. That's... no, that's why I want to be clear. Well-ordered applications. It's where coordination, where you're, it's more like, let me say it, maybe try this way. When you have a highly distributed application, so here's a high bandwidth application. I have a trillion users, and I want them all to go to one website, so I want to have 1 million web servers. I don't need SDN for that, right? Because I just throw bandwidth at the problem. Right? Because the internal state of 1 million web servers are not really related to each other. Right? I can end-to-one peer 1 trillion users to 1 million web servers and just scale horizontally. Right? But when I have 1,000 machines trying to compute one number in a coordinated fashion, ordering in the network becomes a huge factor in terms of, if nothing else is in the way, like disk I/O and other things, ordering in the network can be a very big factor in the wall clock time and in scheduling. So I think those are the properties. It's like wherever circuit switching probably made sense, SDN is going to be more helpful. Oh. Well, I think your question generally points to a really probably all the most fundamental questions in terms of real-world deployments, which is how do we deal with this, a transition to this? Where is it most important? How do we deal with legacy protocols? And I would just direct you to all of the stuff going on in SDN today, because the people who are focused on software-defined networking are attacked, like the Open Networking Foundation. They're asking those questions fundamentally at the standards level and in the deployment level. Yeah. I mean, it's just, yeah. Okay. Great questions.